Okay, time to get started. So, last time we talked about this idea of surface independence, and I just want to remind y'all sort of the big strokes of this. This is a, from a certain point of view, certainly from a computational point of view, more important than path independence. So it's weird, in my opinion, that this is not in the book. This is something that this is an expectation for the course, right? It's not in the book, but it's still officially part of the course, and it's also very much your friend. This is a very powerful computational convenience. Anyway, just a reminder, it's analogous to the idea of path independence, just sort of one dimension up, right? We talked about that. The idea is that if you have one surface and another surface that have the same boundary curve, right? Same boundary curve. Then if the vector field is surface independent, and that's a big if, not every vector field is surface independent, of course, but if it is, then you can just swap out the one surface for the other surface. There's a very nice feature for a vector field to have to be surface independent. Yeah.
Why is it like that? Only the boundary part is why does the rest of the surface not matter?
Oh yeah. Okay. So because here's a nice example. Ultimately, the answer to your question is the definition, right? But I'm going to give you an example of where this comes up, and how this feature is nice. That shared boundary curve. Right? A line integral over that shared boundary curve is what both of these fluxes are equal to. Right? So curls, for example, we know curls are surface independent. And ultimately the reason that we know that they are is because Stokes' theorem tells us that these two fluxes that we're interested in, by Stokes' theorem, they're both equal to a line integral over the boundary curve, and therefore, simply by requiring the boundaries be equal, we know that the fluxes are equal. Yeah. Okay. So but you got to be careful. You have to know that the vector field has this property, and there is. I'm going to get to the punchline on that in just a moment. But not every vector field has this property. Yes.
So that's saying, if they share the same boundary, then the flux of any surface that has that boundary is the same.
If the vector field is surface independent, that's right. So you can take whatever. So I want to show you an example in just a moment. Right. Okay. All right. So. We made an argument on the next page here, and this is a good argument to go through anyway. It's we talked about the details last time, so I'm going to go through quickly. But you draw this picture analogous to a picture that we draw when we were talking about path independence. Right? Draw this same picture, make an argument with Gauss's divergence theorem, and the punchline is surface independent is if and only if the divergence is zero. So this wonderful property, this very powerful computational tool that, hey, toss your surface. You don't need to keep that surface. Switch it to any other surface as long as you don't move the boundary. You can do that if you check this very easy to check condition. Just compute the divergence, right? Straight up partial derivatives. No sweat. Easy to check if you get zero. So we have an easy way to check whether you can use this very powerful tool. And then the example we did was right here. Look at this vector field, that surface, compute the flux, right? If that's the statement of the question, without this idea of surface independence, looking at a flux, I guess we could try to compute the anti-curl, but we don't know how to do that. The surface is not a boundary of anything, so I can't use Gauss's divergence theorem directly. So it looked kind of like you're going to have to brute force this problem. You have to parameterize the surface. Not that that's that bad, but still. You'd have to parameterize the surface and do a pullback, resulting in a double integral over an ellipse, which is going to have square roots and the bounds. It's not appealing, right? There's definitely, it'd be nice to have a different way to do this. And the wonderful solution here is, hey, just check the divergence. Oh my gosh, look at this, it's zero. The divergence is zero, and therefore I can invoke surface independence. I can say, oh, this surface right here, that I was given in the first place, I don't like that surface. I like this surface better. Right? Surface independence allows me to throw away that one and take this one, because of course they have the same boundary curve. And again, very important. Got to have the same boundary curve. Did I see a hand? Yeah, right.
So let's say something is surface independent.
Yeah.
So would that mean that the flux through any given surface with the same boundary curve would be the equivalent to
The same.
the line integral of the circulation?
Yeah, you're leaving out some details. So surface independent means that the flux through this surface and the flux through this surface would be the same because they have the same boundary curve. Yeah. Now, if you want to say line integral, I have to say line integral of what?
Of the anti-curl.
That's the problem, right? We don't know how to compute anti-curl. But if you could find an anti-curl, then yes, point of view could be made that the reason that this flux is equal to this flux is because they're both equal to the same circulation of the anti-curl that we don't know. Yeah. Does that make sense?
Yeah.
Yeah. Okay. Right. Okay. So the way you take advantage of this is you look for opportunities. Look for surfaces such as this one that maybe you don't like for whatever reason, right? And hope, with fingers crossed, that when you compute the divergence, you get 0 and can therefore invoke surface independence. And then pick any surface you like. With the same boundary, of course. Right? Yeah, yes?
So if we compute the surface integral of like a flat surface, can we compute it as a Divergence?
If you compute a flat surface, you have to parameterize it. Right? And now, flat surfaces are typically easy to parameterize. But it is still, unless it is literally part of the XY plane, right, then you gotta write a parameterization. Yeah. Which, by the way, when you do the pullback, will make it a double integral. Yeah, but there are some little detailed doubles about the stretching factor and like the tilt of the plane can matter. And we're gonna do an example along those lines in a minute. Yeah, a little while. Yeah. Right. Okay, so that was one reminder. Now another, as long as we're talking about curl, I think it makes sense to talk about a little bit of physics. We talked about the details of this last time, but there's a relationship between the current field, so the vector field representing the flow of charged particles, and the resulting magnetic field that it creates. Right, that kind of swirls around the current. Right, so, neat fact. Again, this is not a physics class, and so what do you do with magnetic fields, and how does that relate to charged particles and forces and stuff like that? It is not what we're interested in this class. So, but this gives rise to one of Maxwell's equations. So Maxwell's equations. There's 4 of them. This is what I like to call the 4th of Maxwell's equations. Remember, all 4 of Maxwell's equations involve the divergence and the curl of the electric and magnetic fields. Right, so 2 operators, 2 physical vector fields, 4 resulting equations. And so this one being about the curl of the magnetic field. This is equation number 4, and it's that from the previous page. And then we made the observation that that can be rewritten by way of Stokes' theorem as that. So, and likewise, here's another one of Maxwell's equations. The curl of the electric field can be rewritten with Stokes' theorem. Okay. So when you get to E&M classes, or if you've already had an E&M class, you want to kind of maybe revisit some of those ideas just to kind of solidify a little bit. Now that you know Stokes' curl theorem, the connection between these 2 sort of different versions of the equations makes it clear why they're so closely connected. Okay, all right. Okay, and that's where we left off last time. I want to show you an example of how this is useful. So let me zoom in for a moment. So we have a uniform constant flow of charged particles upward. That's represented by this this vector field here, 0, 0k. So the charged particles are moving like this, uniformly and directly upward. All right. Okay. All right. So it makes a B field. Now we remember that the B field goes kind of around, right? And details aside, I'm going to make this assertion that wherever you might be interested in looking, and so let's look at this point right here. At that point, if you were to make a circle that goes through that point, centered on the z-axis, with the circle being entirely horizontal, the B field is always tangent to that circle. And it's also rotationally symmetric, and so the magnitudes of these vectors, all of these points being on that same circle, all same distance away from the z-axis, those all have the same magnitude. Okay. All right, so I'm just going to make that as an assertion, and the question we want to focus on then is, in this situation, what is the magnitude of that B field? So how does the magnitude of the B field depend on the distance from the z-axis? Is it, is it bigger when you get closer? There's temptation to say, hey, maybe it's bigger when you get closer. Right? That's how it works with, like, gravity and stuff. On the other hand, keep in mind, these charged particles are everywhere. Right? So it's not like they're moving just through the z-axis. Okay, so how do we work out these details? All right, so there's sort of multiple steps to this calculation. The first thing I'm going to do is observe that we can compute the flux pretty straightforwardly. So let me first circle. All of this is just a direct brute force computation of flux. We've got, keep in mind, we've got our vector field. I'm going to have to zoom out. Our vector field there, 0, 0k, upward, has magnitude k. This disk that they're flowing through has area, which is just pi r squared. Whoops. So an easy calculation there of the flux. Now, that wasn't the question. The question is, what's the B field? Right? The reason we compute the flux is go back up here. What this equation here says is, if you know the flux, keep in mind the flux of your flow field is current. Right? So if you know that, then you know the line integral of the magnetic field. So it doesn't tell you the magnetic field directly, but it tells us something that relates to the magnetic field, and then fingers crossed, hopefully we can solve for the magnetic field. So let's write that down. And you see down here we have that. That's just Maxwell's equation. Fourth equation, I like to call it. Right. And, now we just kind of have to play with this line integral. Now, looking back up here at the situation, keep in mind that this is tangent to this circle. The B field is tangent to that circle, and that means that B dot T is the magnitude of B. Keep in mind, T is a unit vector. Dot products are magnitude times cosine of the angle. Well, the angle is 0. T is a unit vector, so that simplifies to just magnitude of B. Right. Rotationally symmetric means that this is a constant, factors right outside of the integral in, and all the integral turns into is just a length of the curve. And the length of the curve, of course, is 2 pi r. That's just, old geometry. Okay, now, still, we're not quite done. What has happened here? On the one hand, we computed the left side of the equation. We computed that current, right? And then we also have rewritten this line integral, and altogether then notice that we have that is equal to that and you can solve for what we're interested in, solve for the magnitude of B, and there you go. And what we find is kind of weird. The magnetic field is actually proportional to R. That magnetic field actually gets bigger as you get further out. Kind of weird. Okay. All right. Okay, so just one application there. Okay, so now, per the email that I sent out Wednesday, I guess it was, we're kind of done with Chapter 15, pretty much. Rephrase, we're done with all the individual sections in Chapter 15. But I do want to spend a little bit of time sort of summarizing, what have we learned in Chapter 15? And so, one of the big things that you've heard me saying over and over again is that we're talking about accumulations, right? All the big theorems, 5 or 6 different big theorems that we've talked about, they're all different kinds of accumulations. Here are the various accumulating quantities, right? And correspondingly, each of these 5 or 6, depending on how you count, theorems. The question with the fundamental theorem of line, there's arguably counts twice because there's a version in R2 and there's a version in R3. So we're computing change sometimes, right? Other circumstances, we're computing circulation, such as in Green's theorem or Stokes' theorem, and sometimes we're computing boundary flux. But all of these are accumulating quantities. They accumulate as integrals. Integrals, when you have a good accumulating quantity that is an integral, it's an integral of a density. And the corresponding notion of density, well, that's all of these things. Right now, just semantically, the density associated with change density. Right? Associated with circulation, how about circulation density? Associated with flux, how about flux density? The terminology, very natural, very consistent. Just a quick reminder, though, while this one here is extremely common, and these are certainly heard of, I kind of made these up. Right? I made them up for analogy purposes. I think they're very instructive. I think, if you want to sort of really, if you need to kind of get a foot in the door of how do I kind of get, I need help understanding flux density, then we use the analogy, right? Try to first go back to the fundamental theorem of calculus. We talked about how you can think of the derivative as being a change density. Really digest that first, right? This idea of the derivative being change density. And then notice the analogy between the fundamental theorem of calculus and Gauss's divergence theorem and interpret appropriately. So I think understanding one area can help you understand the other area. So I'm a big fan of that. That's why I introduced a term there. And of course we have names for all these derivative, gradient, Green's operator, divergence, curl, right? They're computed by various formulas and notations. Sure, and that's all details that we talked about going through the course. Okay. All right, so strong analogy between all of these theorems. Don't forget we have these diagrams, and let me just skip forward to the three-dimensional diagram. I like the diagram for various reasons. For one thing, it's just good to have a bookkeeping system, right? We have scads of ideas here in Chapter 15, and being able to organize them in a reasonable way keeps it from being just a horrific mess in your mind, right? So this is a way to organize all those ideas, but it also shows some very strong patterns between, these different theorems. And so we talked about the fundamental theorem of line integrals as being, well, if you take a derivative, you take a boundary, then this is equal to that. And I've done this before, so I won't spend a lot of time on this, but Gauss's divergence theorem, same thing. We realize that Gauss's divergence theorem can be thought of as, well, if you take the divergence of a vector field, the boundary of a solid, then the resulting left side is equal to the right side. Totally analogous. And then finally, Stokes' curl theorem, again, totally analogous. Right? So again, these kinds of patterns, whatever you feel comfortable with about one of these theorems, by analogy, you can help yourself understand the corresponding aspect of one of these other theorems. Okay. All right. Okay. By the way, now that we're done with all of the objects on this diagram, I have a suggestion. I'd like to encourage y'all to memorize this diagram completely, which sounds a little overwhelming, but I think you can do it. In fact, I would not be entirely surprised if you have already inadvertently memorized this diagram, because the patterns are so very, very strong. Now, so a couple of things you do have to actually memorize. You got to memorize which operators go where. Okay, so remember gradient, curl, divergence. If you need to make up a little mnemonic or something, suit yourself, right? But you got to make sure you know where the operators are. Pretty much everything else is kind of, well, what else could possibly be what else could possibly go there? What do you take boundaries of to get surfaces? Well, it's got to be three-dimensional things have two-dimensional boundaries. Two-dimensional things have one-dimensional boundaries, aka curves. One-dimensional things have zero-dimensional boundaries, aka points. That's not really so much something to memorize as something to that you. I mean, I'm going to say, could you possibly forget that? Right? I mean, it's just geometric. It's geometric interpretation. Does that make sense? Okay, so nothing really to memorize there so much. Okay, the operators that we've been dealing with. Well, I mean, come on, we've been doing so much with these. I mean, the fact that when we're talking about vector fields and surfaces, the fact that we're computing flux, well, perhaps you've noticed that we do a lot of flux calculations here, right? So again, I think you've already memorized that. That you know, in this spot in the diagram, we're talking about fluxes, ditto line integrals, ditto triple integrals, etc. Second thing you do have to actually memorize, you got to remember the little pattern that, you know, push forward with the operator, you push effectively kind of backward with the boundary. That's how boundaries work, right? Boundaries take bigger things and give you littler things. And so you have to remember that what these theorems say is that evaluation and that evaluation are equal. Well, that's, again, something we've done loads of, and hopefully, likely, you've already sort of noticed and digested that pattern. Okay. And then I guess the last thing you have to remember is these what I like to call lifetime theorems, that in the, you know, different versions. But, you know, if you're looking at a gradient, then the curl is 0. And likewise, if the curl is 0, then it does have an anti-gradient. Right? So we've done a lot with those. There are sort of various different, there's sort of 4 different versions of these theorems here, but again, they fit together very nicely with this idea that everything has a kind of a lifetime of 2. So vector field, take the gradient, function, take the gradient, get a vector field, take the curl 0, because that makes 2 steps. Right. Along those same lines, if you have something here and if it dies there, oh, well, if that means that's the result of 2 steps, that means that there must have been something over here. Right? So again, pattern. Right? So make sure to understand what the pattern is. And with all of those patterns recalled, I mean, notice everything else is just kind of fill in the blanks. You might surprise yourself. So at some point, after class is over, pull out a blank sheet of paper. If you want to, look at this and kind of, remember some details, spend 30 seconds thinking it through, and then put it down. Clean sheet of paper, no cheating. I'll bet you can reproduce this whole thing. Right? And if you can't, then I think you should get to where you can, because I think there's the ideas, the patterns that it takes to be able to reproduce this are all really important in what we're doing here. So anyway, it's a nice little exercise, and I hope y'all all give that a try. Okay. Let's go back up to the 2-dimensional. Same deal with the 2-dimensional diagram, by the way, so please memorize. Again, not that much to memorize. Gradient is here. Green's operator is there. Pretty much everything else is pattern. And, experience of things we've done a million times. So again, very likely you've already memorized this entire diagram. I have noticed some students doing the following, and I think this is a good idea. Of as soon as the test starts, and I say go, and students they turn over. Of course the back side of the cover page is not graded, right? And you can use that for scratch, and but it's not associated to any question. Reproduce both of these diagrams. Several students have done this in the past, and they just write the whole diagram, or at least enough for sort of pattern purposes, and then they have their little cheat sheet for free to use for the entire exam for your consideration. Okay, so let's talk about, there are some special vector fields I want to talk about here. Let me use so there are some special vector fields. Now we've talked about the special vector fields, some. There's different ways to describe what's special about these special vector fields that I want to talk about. You can say they are gradients of they're gradients of functions, or said differently, they have antigradients. But remember, anything that has an antigradient has this other feature that Green's operator is 0. And remember, Green's operator is a way of measuring circulation density, I like to call it. Right? So to what extent, locally near a given point does the vector field in the plane represent kind of a spinning of a rotating of the fluid, you might say. And so when Green's operator is 0, we describe these as irrotational vector fields. So being a gradient, which, by the way, reminder, the physicists like to call conservative, is the same as being irrotational, regularity issues aside. Okay. And then don't forget we have this third version of, again, these special vector fields, that they are path independent. So if you have any two curves that have the same boundary points, then you get the same value of the line integral. Right, so three different properties held by, regularity issues aside, the exact same vector fields. And so whenever you see a vector field that has one of these properties, you know it has the other two. Right? Everybody remember all this stuff? This is just kind of review. And then the same deal applies in all these other contexts. So let's talk about the same thing in 3 dimensions. There are special vector fields in 3 dimensions, which on the one hand are gradients, which on the other hand have now curl equal to 0. Curl, because that's the appropriate operator in 3 dimensions. Right? And that are, again, path independent, and it looks the same. 2 different paths with the same boundary points, always giving rise to the same value of the line integral. Same deal. And then, likewise, 1 dimension up, special fields in this context. They're not gradients of something, they are curls of something. Right? They're not path independent, they're surface independent. Right? Dimensionally shifted to the right, one sort of notch. And it's, again, appropriate to the operator at this point. It's the divergence that's equal to 0. Right? But analogous, just dimensionally shifted one to the right. Everybody on board? Okay. All right. So here's what I like to call a strategic summary for how to compute line integrals and surface integrals. Which, by the way, of course, again, as you've noticed, is a really big deal in Chapter 15. And by the way, why is Chapter 15 a really big deal? Well, because this sort of stuff, computing line integrals and surface integrals and being able to relate them by way of these theorems, is a really big deal in applications in the real world. It's just tremendously important. Right? I asked an engineer. I know you're not all engineers, right? But a lot of you are engineers. But I asked a engineering professor one time, like, just so I know, for engineering purposes, what's the most important thing to y'all in a multivariable calculus course? And she gave me that the answer that when you talk about real estate, the three most important things in real estate. Do y'all know that one? Location, location, and location. Right? Okay. So anyway, that's their little joke. But anyway, so she kind of copied the joke. She's like, vector calculus, then vector calculus, and then vector calculus. So it's extremely important, just tremendously important. So I think this will be a useful thing for just strategic summary. Someone says here, compute the following line integral. We've got a billion different ideas that all kind of, in some way, may or may not relate to this question. How do you know what order to go in, what ideas to apply? So step one, identify where you are. What kind of an integral have you been asked to compute? Which diagram does it exist in? Where is it in that diagram? Get your context. All right. So, for example, if somebody asks you to compute, and I'm just going to come up to here for visual convenience. Somebody asks you to compute a flux. Oh, okay. Well, you're here, right? And it's good to see and make a mental note of where you are in which you're in the R3 diagram because you were asked to compute a flux through a surface. So Green's theorem's got nothing to do with it, right? That's in a totally different diagram. Everybody on board? Yeah. Okay. All right. By the way, I'm going to need to go back and forth to this diagram pretty regularly, and I should have pulled this up before class started so I can just switch back to it, and I forgot. So let me do this real quick. Take a moment. Let's see here. Okay. Oh, there we go. Okay. Right. Okay, so step one, where are you? Step two, notice there are two candidate boundary theorems that you can deduce just from having previously noting what kind of integral you're interested in. So, for example, if you've been asked to compute a flux, maybe Stokes' curl theorem, maybe Gauss' divergence theorem, but definitely not fundamental theorem of line integrals. So don't play around with trying to find an anti-gradient. Right? Everybody see the point there? And two reasons, by the way, I mean, keep in mind, there's, for one thing, it's a waste of your time, right? It's clearly irrelevant. Anti-gradient, if you're computing a flux, who cares? It's got nothing to do with the problem, right? The other thing is, keep in mind, it's not just a question about whether you do or don't get the right answer in a box down at the bottom of the page. I'm looking at all of the work. I'm interpreting from what you write, how well do you understand the ideas that are relevant to this question, right? And if you're off doing things that at casual glance at the diagram you should realize are completely irrelevant, it doesn't look good, right? So please, make a point of don't write anything down that's couldn't possibly help. That's not a good thing. Okay. All right, so here's your two candidates. Stokes' curl theorem, Gauss' divergence theorem. Okay. Compute the operator that the diagram tells you to compute. Now, what do I mean by that? Let's go back to the diagram here. You've been asked to compute a flux. Perhaps you've been given a vector field and a surface and asked to compute a flux. What does the diagram tell you to compute? Well, they gave you a vector field. You know, by virtue of the fact that you're here, that the vector field is there, and therefore you should compute that. Okay, so the diagram is telling you to compute divergence. So go ahead and do that. Right, it's an easy calculation. Okay. All right. Eraser. There we go. Okay. And then think about which, as a result of that, which boundary theorems might apply. So, for example, coming back into here, suppose you compute the divergence, and suppose you get not zero. Well, if the divergence is not zero, that means that there is no anti-curl. If there is no anti-curl, you cannot use Stokes' curl theorem. So that's not a candidate. Right? And it doesn't even apply. Not only can you not find the anti-curl, there is no anti-curl. Okay. On the other hand, if you do get zero, that means there is an anti-curl, and you might be able to use Stokes' curl theorem. Now, again, it's annoying. We don't know how to find the anti-curl, so probably not. But anyway, it's on the table. Okay. All right. Now, what about, again, if we're looking at a flux, does Gauss's divergence theorem apply? And again, lots of students tend to kind of rush to judgment on that, sort of just immediately. Whenever they see a flux, they say, equals triple integral of divergence. Right? And again, you can't do that. Gauss's divergence theorem does not always apply. You need, for that surface to be the boundary of something. Said differently, there has to be an anti-boundary. Again, more terminology that I think I may have made up on my own. But it makes sense, right? It fits in context. So, think about that, right? Don't proceed forward in computing a flux. Give me 2 seconds. Before you've even thought about the question of whether this surface may or may not be a boundary of something. If it is a boundary of something, then you've got another candidate theorem that might be exactly what you need to answer this question. Yeah.
So you can theoretically use Stokes' curl theorem to calculate flux.
Mm-hmm. Yeah, but that's right. If you know if you can somehow or another, if you can find an anti-curl, and these situations arise sometimes, if you can find an anti-curl, then yes, absolutely. Yep. Okay. All right. Now, if the theorem on the left applies, if the theorem on the right applies, or one or the other, you can just proceed, and that's fine, right? There's nothing really wrong with that. But I want to encourage that you consider all of your options before you just plow forward, because a different option might be better, right? So think about path independence. Think about surface independence. Going back to the diagram, if you're looking for a flux, and if the divergence is zero, hey, you've got a surface independent vector field here. Look at your surface. Think about how you might be able to push that surface around a little bit. Again, don't move the boundary. You got to leave the boundary where it is, right? But you can push, pull, whatever, flatten out, play with that surface any way that might be convenient, and completely redo the problem. It might just fall into your lap. It might just totally solve the problem for you to use surface independence. Right? So consider that possibility. Likewise, here, consider the possibility, if curl is zero, hey, path independent, who knows, maybe changing path might be the big option. Less likely, right? Because again, fundamental theorem of line integrals, really easy to work. So, anyway. Okay. Every so often, again, you get geometrically lucky. Look for that possibility. Maybe your vector field is just sort of obviously perpendicular to the surface, parallel to the surface through which you're trying to compute the flux. Your answer is zero, right? So heads up, right? You never know when the question might be a freebie. So always think about that. It's worth a shot. And then once you have your various options, so you may or may not have a boundary theorem or two to consider. You may or may not have path independence or surface independence. There may or may not be some geometric good fortune that might make the problem easier. You're going to have several candidates, and do whichever one looks easiest. And then always keep in mind the possibility that maybe, I thought this was going to be easy, but this is working out pretty ugly. Maybe try one of the other ones. Right? Keep your options in mind. Okay, so I have some examples prepared that I want us to go through. Let's take these one at a time. We want to compute this line integral. We've got a vector field given, curve given. Oh, by the way, the curve is parameterized. Again, there's that urge per section 15.2 to plug and chug, right? You want to resist that urge. Certainly in this case, look at that parametric curve. Look how ugly your x, your y, and your z are. Imagine plugging that into that vector field. This is going to be a nightmare if you brute force it. So let's not. Right? Okay, well, let's consider, let's follow our process. Where are we? We're computing a line integral. Are we in R2 or R3? R3, because there's 1, 2, 3 components in the path. So line integral in R3. So we are looking for one of those. Diagram says compute curl. Everybody on board? Okay, so let's do that. By the way, my little cheat. Remember, curl is del cross. A cross product is computed as a symbolic determinant. I like to just... why is my little pen not working here? There we go. Why? Right, and so... the first component of the curl is the y partial of the third component minus the z partial of the second component, right? You can kind of go through like that. I just find that you don't even have to write this up here. You just kind of visualize those up there, and then you see y partial of that minus z partial of that. Yeah, you had a question?
If you can see that there's an antigradient, you have to still...
No, yeah. If your inner oracle speaks to you and says, here's the antigradient, you can just write that down. I mean, you would want to clearly, indicate that I mean, keep in mind, it's not about answers, it's about process, right? And so you want to put on the page, compute the gradient of the thing that you have just seen as being the antigradient, right? Because we need to know that you know. Yeah. But, yeah, it's totally fine. But anyway, if you can't just sort of see that here, y partial is 1 minus z partial of that is 1. So we have 1 minus 1. That's 0. Cool. Z partial of that is 2x minus x partial of that. Also 2x. We have 2x minus 2x. That's 0. And then likewise, third component is 2y minus 2y. Also 0. So the curl here is 0. Yeah, everybody happy? Okay. By the way, here's another. Keep in mind, I'm looking for evidence of comprehension and proficiency, and understanding the ideas that are going on here. Please make sure to write these objects down correctly as type. Please don't write. I mean, I see this happen sometimes. 0 plus 0 plus 0 equals 0. It's not plus, right? Curl is not a scalar. That looks really, really bad. Everybody see that? So be careful, right? Make sure to write your things correctly. If you want to just write it as 0 vector, fine, totally fine. But don't give any dead giveaways that you've misunderstood the object that you're applying. Okay. So back to the diagram. We took the curl. We got 0. That means we've got some options here. I can use the fundamental theorem of line integrals. That's a strong option. I can use path independence, but really, honestly, given my choice, I think fundamental theorem of line integrals is easier to work with. So let's do the fundamental theorem of line integrals. But before we do, last thing to consider, maybe I could use Stokes' curl theorem. I mean, we already computed the curl. Why did I erase it, by the way? That was silly. What do you think about Stokes' curl theorem? Oh, by the way, especially given that the curl is 0, how about this? We'll just say flux curl dot ds equals flux of 0 equals 0. Bam. How's that? What do you think? Anybody like that one? Can you tell from my tone that you shouldn't trust me right now? Anybody want to tell me what's wrong with this? Landmine. It is. This is totally a landmine. Do you want to elaborate? No? Oh, so you're just psychoanalyzing me, I think, is that right? Okay, so this is absolutely a landmine. Okay, if you write this down, gosh, I'm sorry, but very little of what's written down here is at all meaningful in the context of this question. So look at the curve, right? This curve may or may not be a boundary. You need for that curve to have an anti-boundary. You need the curve to be the boundary of something if you're going to write this down. And this curve, now this is a wacky curve. I can't draw this curve, but I can easily plug in t equals 0. I can plug in t equals 1 and do some arithmetic. And what you find is that the starting point and the ending point are not the same point. So this curve, wacky though it may be, does not close. It can't be a boundary of anything. That means that there is no surface. Therefore, flux through what? This is meaningless garbage. That, just there's nothing about this solution that I've written here that's right. So heads up for the landmine. Make sure that you don't step on the landmine. If you're going to apply a theorem, sort of on the right-hand side, you've got to make sure that there is an anti-boundary. Otherwise, you're writing down garbage, yes.
So in the case of a curve, you can see if it's closed by plugging in, the t. But if we want to see, a surface is closed,
then you have to understand the surface. And how surfaces are described, it's different in every problem. But if you were going to make that, if you want to do that, you've just got to make sure that you understand confidently and clearly what the surface is, and then once you have an understanding of it, then it's either clearly closed and therefore a boundary or not.
So
but
it won't look complicated.
It won't be. Well, I mean, whatever it is part. Part of understanding surfaces is part of this course, right? And so there's a bunch of different techniques, and you have to step one understand the surface, and then again it should be geometrically clear whether it is or isn't. Okay. All right. We're short on time, so let me move along here. Okay, so I suggest that we stick with fundamental theorem of line integrals, find the anti-gradient. That's arithmetic. You guys can do that. I'm going to move along to the next one. What do we do in the case of this one? By the way, is that the same? What's going on here? Is that the same curve? It looks a lot like this. Oh, no, it's different. This is sine instead of cosine. And this is a minus instead of a plus. Okay, so it's not quite the same curve. So what we thought we knew about the previous curve, not necessarily the same here. And let me just go ahead and give it away. Plug in 0, plug in 1, you get the same point. That means that this curve, wacky though it may be, starts and ends at the same point. So Stokes' theorem is on the table. Yeah? Okay, now here's let's consider the other option. By the way, I kind of skipped ahead. So line integral in R3, and there is an anti-boundary, so this is an option. Next thing we need to do, compute the curl. We need to see, do we get 0 when we compute the curl? By the way, notice how the diagram is just, it's organizing all of our options and choices for us. It's very convenient. I want to encourage y'all to rely on this diagram a lot. So we take the curl. Y partial of that, 0, minus Z partial of that, 0. Z partial of that, 0, minus X partial of that, 0. All zeros. By the way, easy to notice before you even start taking partial derivatives in this case. Because this is all X's. This is all Y's, and this is all Z's. Right? And so all the partial derivatives that you're going to do are what you might call off partials. I'm never going to be taking the X partial of this, just the Y and Z partials, and there's no Y's and Z's. So at a glance, you can see that the curl is equal to 0 here. Is that cool? Okay. On the other hand, well, anyway, so yeah. So the curl was 0. That means we can use the fundamental theorem of line integrals. So you have two options in the case of this question. On the one hand, you could say flux through the surface of curl F dot ds equals flux of 0 equals 0. That's fine. Right? Or you could say, because there is an anti-gradient, f of b minus f of a, but a and b are the same, so this is equal to f of a minus f of a, which is 0. Yeah? Everybody okay? So two perfectly valid, two perfectly fine solutions to the problem. One little issue, you could quibble here and say, yeah, but, what is that surface? Likewise, quibble on the other side, yeah, but what is this function? Right? Finding that function, taking an anti-partial of that with respect to x is going to be irritating. Right? So, anyway, the little quibbles on both sides, but both of these as strategy are fine, yeah.
So, you said that Stokes can apply on the second part because it becomes a closed surface.
Yeah, it's a closed curve, and therefore it's going to be the boundary of a surface. That's right. And again, this is technically, there's little issues, annoying issues of what if it's closed, but only after having tied itself in a knot in a weird way. And again, these are issues that can be dealt with. And almost, it would be very hard to write a problem that actually applied to. So yeah. Okay, and sadly I'm out of time. So we will pick up here on Monday. One last announcement. So on Monday we are going to do course evaluations. So make sure to bring something that you can do course evaluations with. The administration recommends. By the way, the administration as much as requires us to spend class time on this. Right? Because otherwise response rates tend to be really, really low. So bring something. They recommend that you bring a laptop because typing works really well, right? But if you can access it from your phone and if you're comfortable doing it that way, I think that's also fine. Okay, see y'all later.